Hi, my name is Yiyun.
And I'm James Parker. Today we're presenting our work on verified replicated data types using refined type classes in Liquid Haskell. This is joint work with Patrick Redmond, Lindsey Kuper, Michael Hicks, and Niki Vazou.
First, let's talk about the motivation. Our goal is to build verified distributed applications that's readily executable. Liquid Haskell is a promising solution built upon an industrial-strength program language, Haskell. Unfortunately, Liquid Haskell does not support type classes, which are an essential abstraction for modeling distributed data structures. In the process of seeking a solution, we ended up making the following contributions. We extended Liquid Haskell with support for refined type classes. We verified the Typeclass Laws for 34 instances of 5 widely used type classes. We implemented a model for replicated data types and proved the strong convergence property. Based on those data types, we built 2 distributed applications, an event calendar, and a collaborative text editor. James and I will showcase these 2 applications near the end of this talk. Next, I'll give some background on Liquid Haskell. Liquid Haskell is an extension of Haskell. It allows programmers to decorate plain Haskell types with refinements. In this example, we have the head function, which takes a list and returns its first element. Liquid Haskell will ensure statically the precondition that the input list is non-empty to prevent the runtime error caused by trying to access an element from an empty list. When refinements are simple enough, as in this case, SMT can automate type checking without any intervention from the user. Liquid Haskell supports intrinsic proofs, where properties are directly encoded in the type of the function that we're interested in. In this example, we have the list concatenation function, and the post condition specifies that the length of the returned list is equal to the sum of the length of its 2 inputs. In many cases, Liquid Haskell can automatically prove the attached property, and the user can just define their functions as they normally would. And here we want to show that list concatenation is associative. Since it involves 3 elements, it would be awkward to encode the property directly as a postcondition of the concatenation function. Instead, we use the extrinsic style and define the property as a separate theorem. The proof is manual induction over elements of the first list. And thanks to the mechanism called refinement reflection, the proofs can be written as ordinary Haskell functions. Next, let's talk a little about type classes. Typeclass is a mechanism that was first introduced in the 80s by Vazou and Blot. If you're already familiar with Java or Rust, it's actually kind of similar to interfaces or traits. A class specifies an abstract interface for different data types, and the instances provide the actual implementations. In this example, we have the semigroup class with a binary operator as its only method, and the list instance implements the associative binary operation as list concatenation that we've defined in the previous slide. We can also use type classes polymorphically by adding class constraints. In this example, we are allowed to use the binary operation inside the body of append 3 because we require A to be an instance of semigroup. GHC, the standard Haskell compiler, converts Haskell code into a simplified representation named core. Interestingly, type classes don't actually exist in core. Instead, they're compiled into dictionary types. On the left-hand side, we have the class definition in Haskell, and on the right, we have its corresponding dictionary representation in core, as a dictionary type with only a single field, the binary operation. Similarly, instance definitions are converted into values or inhabitants of the corresponding dictionary type. Type class constraints are nothing but extra dictionary arguments to a function. Note that the fat arrow in the type signature append 3 is turned into an ordinary function arrow because semigroup is just a data type in core. With all the implementation details, let's go back to something higher level. As programmers, we want to specify not only the operations that a class supports, but also the laws that its instances must obey. For our semigroup example, we don't want an arbitrary binary operation, but a binary operation that is associative. Unfortunately, there's no easy way to enforce laws in plain Haskell. Instead, laws are specified as part of the documentation. To address this limitation, we introduce the concept of refined type classes. Remember that at the beginning, we were able to refine signatures of ordinary Haskell functions, such as head and concatenate. What if we can do the same with class methods? In this example, we define V semigroup, as shown above, a subclass of semigroup, which inherits a binary operation, but also adds an additional method, which encodes the associativity law. Every time an instance is created, we want Liquid Haskell to check that it satisfies the associativity requirement. Liquid Haskell verifies the core, where type classes do not even exist. Instead, we have V semigroup as a data type, as shown on the screen, where P1 V semigroup refers to its superclass dictionary, while law associativity is the actual law method that we've added. Fortunately, Liquid Haskell does know how to verify refined data types. At the bottom, we have the refinement for associativity, but we can't just attach it directly to the data type because it is missing the explicit dictionary arguments. Our solution is to converge the refinements to core expressions. We take the user-provided class refinement, then ask GHC to type check the expression. During type checking, the expression will undergo a process called elaboration, where the resolution algorithm fills in the correct dictionary arguments. After type checking, the binary operation is now explicitly applied to P1 V semigroup, which corresponds to the parent dictionary stored in V semigroup. With a bit of cleanup, we can attach the refinement back to the core representation of V semigroup. At this point, we have successfully converted a refined type class into a refined data type. Recall that instances correspond to values of the dictionary. When we invoke the CV semigroup constructor to create a list instance, we have to pass in the associativity proof we have done before for a list concatenation. Otherwise, Liquid Haskell will complain that the law is not satisfied. To evaluate our extension to Liquid Haskell, we conducted 2 case studies. In this case study, we verified the class laws of 34 instances. As we can see from the table, we verified the most commonly used type classes in Haskell. Thanks to the automation offered by Liquid Haskell, the length of the proofs and the verification time are both reasonably short. Next, I'll let James talk about the case study of replicated data types.
We used our extension of Liquid Haskell to verify properties about replicated data types. Conflict-free replicated data types are used in distributed systems to replicate state across multiple nodes without conflicts. These data structures have special mathematical properties. Specifically, operations on these data structures must commute. As an example, consider the sum or counter CRDT. Initially, Alice and Bob both have a state of 0. Alice locally adds 21 to her state, while Bob adds 42. Bob sends the add 42 operation to Alice, and Alice sends Bob her add 21 operation. In the end, they have the same final state of 63 since addition is commutative. Here's the definition of our verified replicated data type typeclass. Op, which is a type family, is sort of like a type level function that specifies the type for operators on the given VRDT data type. Apply is a function that takes a given state, applies an operation on it, and returns the resulting state. Compat is necessary because some VRDTs have special requirements, like each operation must have a unique identifier. Law commute encodes our commutativity property. In particular, applying an operation op1 and then an operation op2 results in the same final state as applying op2 and then op1. Here's an example VRDT instance. This is the max instance, which just keeps track of the maximum value ever seen. Operations for max are just max itself, and apply just takes the greatest value. All max operations are compatible with each other, and the proof of commutativity is trivial, so Liquid Haskell will automatically perform the proof for you. We implement a proof of strong convergence, which is a safety property that's required for all replicated data types. In this proof, we have an initial state, S0, two lists of operations, ops1 and ops2, and we have a precondition that ops1 and ops2 must be permutations of each other. Our refinement states that the list of operations may be applied in either order, but the resulting state will always be equal. We implemented and verified many primitive VRDTs. Multiset is a collection of values with an associated count, and causal tree is an ordered sequence of values, which is typically used in collaborative text editing. We also implemented compound VRDTs, which are special VRDTs that can be composed on top of other VRDTs. For example, we implemented a two-phase map VRDT, which provides a mapping from keys to values. Values must be a VRDT instance itself, and once a key is deleted, it cannot be re-added. At the top, you can see the operations that are available for a two-phase map. You can insert a key or a value, you can delete a key, or you can apply an update to a specific value for a given key. Users can create their own VRDTs by defining custom data structures that are composed of existing VRDTs. Our library automatically derives VRDT instances and their proofs for these custom data types. This is done at compile time using template Haskell. As an example, consider the event data structure at top, which is composed of last writer wins registers for the title, description, and start time of the event, and a multiset is used for the RSVP list. This summarizes the proofs we did for the VRDT instances. Most of the instances were trivial, and Liquid Haskell was able to automatically verify them quickly. The strong convergence proof was a couple hundred lines of code, while the multiset, two-phase map, and causal tree proofs were more substantial. We built two realistic distributed applications using our VRDT instances. The first is a shared event planner, which uses the event data type that we previously saw. The second is a collaborative text editor. We also implemented a server that propagates operations between all of the clients. Our implementation also integrates with Reflex, a FRP or functional reactive programming library, to build a terminal interface. Every time an operation arrives, the interface updates automatically, so VRDTs and FRP interact really nicely. Yiyun and I will now demonstrate our example distributed applications. The first is the shared event planner. So I'll launch the client application, and you can see that we've already created an event for OOPSLA. Unfortunately, the location is incorrect, so I'll edit this. And it's now been updated for Yiyun as well. I'll create a new event. Let's have a Thanksgiving dinner. I'll bring turkey to the dinner. And let's create our event. So I'll RSVP. And Yiyun has RSVP'd, and he's indicated that he's going to bring pie to the dinner. So now I'll run our collaborative text editor. So this is a collaborative text editor. Its convergence properties are fully verified. Oh, Yiyun fixed my typo for me. So hi, Yiyun. And you can see we can both edit real time together, even though we're about 30 miles apart right now. In summary, we extended Liquid Haskell with support for refined type classes. The source code is available online, and we're in the process of merging it into the main Liquid Haskell repository. In addition, we verified 34 common instances of the center group, monoid, functor, applicative, and monad type classes. Finally, we defined a new model for replicated data types, implemented many VRDT instances, proved strong convergence for all of them, and implemented 2 realistic distributed applications using the VRDT instances. The source code is also available online. Let us know if you're interested in verifying additional replicated data types or building distributed applications using them. We're happy to help. Thank you.